everyone's settled, maybe we'll just jump into it.
We didn't say that anyone was allowed to interact at this point. I'll give a quick intro to Armon. Obviously, co-founder of HashiCorp. I think we're pretty lucky to have him in town. I just got to spend 45 minutes with him having a one-on-one chat that we plan on publishing later this week, so that was a lot of fun. So I just say on behalf of the community, thanks for your software and driving the community to write great software. So without further ado.
Awesome, thanks so much, and thank you guys for being great partners and hosting this. Definitely couldn't have done it without their help, so appreciate it, and thank you all for making the time. So I know Tim has done the brave work of actually doing a live demo. I'm gonna take it a little more easy here, but I figured I'd talk a little bit more kind of high level around what are some of the challenges we're seeing that are sort of driving service mesh, and then I think you saw the hands-on of how do you actually implement and sort of use it in a Kubernetes environment. Sort of look more on the flip side of sort of architecturally how does this work and sort of the why behind some of the design choices. So I think you got a little bit about me. If you have any follow-ups, I'm easy to find. I'm all around the internet as just Armon. So please get a hold of me if you have any questions or follow-ups from this. And given that this is a hug, this is sort of home turf for HashiCorp, I'd say. So you probably don't need much explanation about the stack, but for folks that maybe know one or two of the tools, but not sort of the whole thing. In general, we kind of play in these four main categories, right? One is thinking about how do we actually provision and stand up infrastructure sort of day one, day two, day n when we decommission, right? And the big focus for us is Terraform, but Vagrant and Packer exist in that bucket as well. And then sort of from a security perspective, how do we think about infrastructure security, application security, data protection, and big focus there is Vault. Consul, obviously what we're going to talk about today, more networking oriented around how do we wire together all of these different pieces. And then the kind of final piece is Nomad, which is sort of the deployment tool that sits on top of it all. So what's the abstraction we kind of give developers as they deploy their applications? So the thing I'd be remiss to not mention is we have two major conferences this year. So if you like geeking out about sort of HashiCorp toolset and how they can be used and sort of best practices and all that kind of good stuff, there's two this year, right? One is HashiCorp EU in Amsterdam, only sort of 2 months away now in June. And the other one, a little less travel involved, is Seattle in September. So this one is sort of the flagship event. It'll be probably like 1,200 people this year. And it's usually a great time. So would love to have you guys join us. Okay, so on to sort of the topic at hand. I guess part of what makes it useful to sort of talk through this is what's the transition that we're seeing kind of everyone go through here, right? I think historically, if we talk about application architecture, there's very much the kind of classic monolith, right? So the example I'll use is, call this box desktop banking, right? And A is maybe the login service, B is check balance, C is, funds transfer, D is bill pay or something like that, right? Within the organization, you'd probably have a different team developing each of these pieces, but we're going to sort of compile it as one giant monolith and release it as one application, right? So I think there's nice things about this architecture, right? One nice thing is if subsystem A needs to interact with subsystem B, it's easy, right? It's an in-memory function call. It's just looking up for the function pointer, it's jumping in memory, life is easy and fast, right? If we need to kind of go out of the process, typically we're going to go talk to an actual database, and we're just going to hard code, go to the static IP, or it might be the IP of the database, might be the IP of a load balancer in front of it, but that'll be roughly the kind of sort of routing that we need to do, right? As we need to scale this system up, there's really no way to say, well, I need more of my login service and less of my sort of check balance, right? It's all one monolithic application. So you just run more copies of the full monolith and then just put a load balancer in front of it and shard traffic across it. Right? So there's really no way to say I need 10 of A and 2 of B type of a thing. And kind of the final piece of this is how do I secure the whole thing? In practice, what we tend to see is sort of a zone-based architecture, right? So if you kind of scan left to right, you might have your sort of DMZ zone, right, with the internet facing, then your application zone, and your sort of data zone. And it will kind of assert that each zone can only talk to the one immediately to its right. So some amount of sort of segmenting of traffic and making sure it only kind of flows in one way. So going from that, you're like, okay, that seems great. Seems like we sort of sorted out all the problems, right? Why bother change anything, right? I think the first kind of big shift is really application pattern, right? So we're going from monolith to really saying, actually, we're going to explode this out into sort of a series of smaller microservices, right? And there's a lot of advantages, right? We can spend the whole hour talking about that trade-off alone, but it's really one about application agility, right? It's, okay, if we're all releasing as one super monolith, then A, if there's a bug in login and they need to patch it, right, they need to wait until B, C, and D are all in a ready state that's integrated, and maybe it takes 3 weeks to actually do a rev of the monolith. Versus in this model, if A doesn't break their contract and it's just a bug fix, right, they can patch the bug, ship it out, and sort of no one's any wiser, right? So it's sort of each team can kind of run at their own speed, right? That I think is the kind of the biggest trade-off. Now with that, there's like sort of no free lunch, right? So sort of what we gained in sort of developer agility, we sort of almost lose in equal measure with operational complexity, right? So the first challenge that sort of comes right away is, okay, what if subsystem A wants to talk to subsystem B? Before it was easy. I mark a method as, public, or I export it. The other side is just making a function call. Now B lives somewhere on the network, right? It's not the same app, it's not the same machine, it's somewhere, right? So how does A actually discover and route to it, right? So kind of the first challenge is the discovery one. And in practice, you probably don't have one copy of B, you probably have many copies of B, either for scaling or availability, right? You don't want one thing to go down and take the whole service, right? So the challenge is, now what does A do, right? In practice, what we tend to see is put a load balancer in front of every service tier, hard code the IP of the load balancer, and just have 500 load balancers all over the place, right? It's the kind of default. And so it's like, okay, that's already bad, right? And then sort of layer onto the pain, right? Kind of two transitions at the same time, right? Obviously the one to cloud, which is just, the failure rate is just much, much higher than what you would see with hardware running in a data center, right? You just think about this stuff as much more ephemeral, right? So the classic Netflix, sort of chaos monkey, right? Type stuff of design around the failure as the expectation, right? The other side of it is when we talk about containers, in general, we're talking about even more dynamic infrastructure, right? We're saying we're going to run it in Kubernetes, we're going to run it in sort of these environments where, great, the scheduler might decide it's on this node, 5 minutes later it's rescheduling, moving it somewhere else, versus a static VM where you schedule it and for the next 2 years it's on the same machine, right? So much, much more ephemeral in terms of how often we're dealing with network changes, plus our topologies are just way more complicated now, right? So all of this sort of brings us to sort of, okay, how do we think about what changes in sort of the networking land around the services? And I think the first big one is service discovery is kind of a first-class concept, right? So you can kind of fill this in different environments, right? If you're talking about the Kubernetes environment, for example, as Tim pointed out, there's sort of an existing registry concept, right? The moment any pod gets launched, it exists as part of a global catalog, right? We can query it anytime and say, what are the pods running, filter on labels, things like that. This is the general concept of a service registry, right? Is that when things kind of get deployed, they get populated, they get registered as part of this thing. And at any time, we can go query this thing and say, hey, tell me about where my upstreams are, right? Where's B running? I want to go route to it, right? So this can be exposed in a number of ways. Consul exposes both DNS as well as an HTTP API, but logically, you're doing a query against a registry, right? And what this enables us is then to do this sort of direct connection. We don't need to hard code the IP of a load balancer that then takes us back. We can query the registry, dynamically figure out what are the IPs, and then go directly to the instance behind it, right? Oops, I don't know what the heck just happened there. Let's skip like 10 slides ahead. Okay, so the thing that's sort of always been sort of an exercise left to reader has been, what happens if it's not the intended downstream that's doing this discovery? It's just someone on the network, right? An attacker happens to be on the network. They say, tell me where B is, and they go connect, right? And I think the sort of exercise left to reader has always been, you figure this out, right? Sort of segment your network in such a way that traffic can't get to B from an attacker, and therefore it's not the registry's problem, right? And so I think this brings the topic of service segmentation up, right? We've always said segment your network, solve it at that layer. So the question is, okay, what is service segmentation, right? There's a ton of jargon in this universe, but effectively, it's all a very simple idea, right? I have a physical network, right? Physical in some sense, right? If I'm in the cloud, it's sort of logical itself, but I might split that sort of physical network into smaller logical segments and then isolate them from each other, right? So I might say I have one network, but segment A is dev and segment B is prod, and these two should never meet, right? Even though they might be running on top of the exact same set of Cisco switches, right? It's a shared underlying infrastructure. We're logically segmenting it. So the common sort of approaches to this is on-premise would be something like a virtual LAN, right? You sort of tag the packets. Are they dev or are they prod, right? Doing firewalls to sort of split these zones, software-defined networks. So you can kind of put all the cloud networks in that last category, right? If I describe a VPC, two VPCs they're logical. They're on the same network, right? And what you tend to see is this kind of segmentation is very coarse-grained, right? If I look at sort of a zone, right, and say this is my production zone, you might still have thousands of machines, thousands of applications in that one zone. So your blast radius is still pretty large, right? So if we sort of map that back onto sort of the classic architecture, you would describe this as saying I have kind of three segments, right? The DMZ, the app zone, the data zone as the major segments. So now the problem is what happens when we modify that middle zone to better reflect sort of a microservices architecture, right? It's no longer a single monolith, it's many services now that are interacting with each other in a complex way, right? So before we had a pretty clean left to right flow, right? Traffic came in, hit the load balancer, went to the monolith, went to the database, and went back. We're now in this middle zone, there's sort of a more complex flow, right? We have to worry about these different paths, and it's not really obvious, like, where would I put a firewall in this thing, right? And it's a small enough example that you would just say, you know, screw it, put a firewall in front of all of them, right? And you can kind of get away with it. The reality, though, is, you know, as you start to look at real organizations, it doesn't look like that, right? You know, even this is still a pretty trivial example, right? If you pick, you know, pick Bank of America, that middle category is 4,000 applications, right? So yeah, you can look at 4 and say, okay, here's where I'd put the firewalls. You'll start looking at 4,000 and you're like, yeah, there's no way, right? Or you're gonna need 4,000 firewalls that you're now managing, right? Which is its own pain. So this is really the practical reality as you start getting service-oriented. I think, you know, Adrian Cockcroft from Netflix sort of famously calls it sort of the Death Star architecture, right? As you have enough services and draw the graph of their interconnects and it just looks like the Death Star, right? Everything connects to everything else. And so I think, you know, if you step back and say, okay, well, what would we ideally want, right? We'd want the networks to be as tight as physically possible, right? I'd want my logical segment to just encapsulate, you know, A and B because they need to talk to each other, and C and D. The problem is, you know, the world exists to frustrate us, right? So, you know, in reality, you have, okay, well, A also needs to talk to C and B also needs to talk to D. So there's no easy way to do that clean division, right? So in practice, what we end up doing is saying, we'll just zoom it out a level, right? We'll just click up a level until all 4 of the sort of connections can be satisfied, and we'll just put all of A, B, C, and D on one coarse-grained network, right? And you just repeat that enough times until you discover that all of your services are in one production network, right? So that's sort of a good tee up to sort of Consul, right, and sort of the problem space we look at, which is really almost kind of 3 different pieces, right? Very related, but kind of independent still, right? The first one is service discovery, right, and we'll talk about that in a second. The other is service configuration, right? So almost orthogonal entirely to this stuff is what happens if I want to have kind of runtime configurations for my apps, right? I want to be able to change settings sort of while the app is running, and I don't want to redeploy the app, right? You kind of need sort of an online database, if you will, to be able to do something like that. And then the final piece is the segmentation. The final piece is the segmentation around governing who has access to what, right? So for folks that are unfamiliar with Consul, it's sort of it's interesting because I almost feel like there's been a second launch of Consul in some sense, right? It was originally launched in 2014, really looking at the service discovery side of things. And I feel like, you know, it was a hit then as it seems to be a hit now. And it was really at that time looking at, great, as we adopt this sort of more DevOps-y pattern, the problem is statically coded IPs are fragile, right? So this is sort of, you know, 2014 sort of predates Docker and containerization, but really even then, as you were saying, hey, we're going to use Chef and, you know, Puppet and want to sort of deploy our applications in a much more nimble DevOps-y way, the problem was hard-coded static IPs breaks everything, right? So Consul sort of filled that gap. And so as a result, it's, you know, pretty massively broadly used and downloaded, right? We have individual customers with, you know, over 50,000 agents. And when you kind of look at the set of people who talk about it and use it, I think one thing that's sort of interesting you'll find is there's not one really stereotypical mold, right? You can't look at it and say, oh, it's only sort of mega enterprises, right? That discounts small people like Stripe and Twitch, right? You also can't say it's only people born in the cloud, right? Because then you're like, okay, well, UBS literally maintains like vaults in Switzerland, right? And so you have this sort of whole spectrum of super legacy on-premise people like UBS and SAP Ariba to super cloud native, you know, born in the cloud type players to DigitalOcean, who quite literally is a cloud, right? So it's kind of this whole gamut. And I think the reason for that is as long as you have more than, call it a handful of services communicating over the network, you have all of these problems, right? Like, congratulations, you now have a service mess, right? So how do we actually deal with this, right? Turns out at sort of every architecture point we have it. So I think the kind of first piece of this is the discovery component, right? And it's really, what Tim showcased is about having that registry of what are all the nodes that are running, what are the services running on top of those things, what's the health status of all of those things, and having this sort of global view of everything that's actually running, right? So Consul exposes this in kind of a few different ways. One is over DNS, as we saw, right? You can just query it as, give me redis.service.consul, right? The other is a rich HTTP API, so this starts to let us do kind of more interesting automation on top of Consul. And then the web UI, which you saw, lets it be a little bit more human-friendly. So we'll kind of power through this pretty quickly because I think you guys saw this already, right? Here's a really basic DNS example. Effectively, you just think about, sort of a shift Consul's making is instead of thinking about DNS as sort of a static zone record that I manage, it's really a database of what's running and sort of a convention around how DNS queries map onto that. So you almost can see how this translates literally to select star from services where service name equals Redis, right? Is effectively what is happening, right? We're doing sort of this translation between here's the DNS query and what's the internal query against what we should return. So you can get much, much more sophisticated. This is sort of a basic thing. Consul can use DNS even to do things like, nearest neighbor failover between data centers, right? So you can start to get super fancy and say, hey, I want Redis, but if it's not available in my data center, find the nearest one based on latency and do a failover and route me there. So you can get pretty sophisticated in terms of how Consul translates what seems like a simple DNS query into the result. The other kind of equivalent view of it is what if I query the HTTP API, right? So now I'm going to get a whole lot more information back. Before I just got the IP back, now I can get all sorts of, what's the ID of the thing it's running on, any metadata, tags, all sorts of good stuff like that. So this ends up getting used either by rich clients, right? Clients who want to natively query Consul and do load balancing in a more intelligent way. Or if I'm driving more interesting automation, right? I want to consume the whole catalog and use that to drive other things, right? The HTTP API is much richer than you'd get from DNS, right? Oops, I don't know why this keeps happening. The web UI you already saw. Really, it's just meant to be pretty and usable, and our designer Hannah has done an incredible job. From if you ever saw sort of Consul V1's UI, you're nodding, right? V1 was like, you're like, oh, the guy who designed Craigslist, he must work for HashiCorp. So it's come a long way. The other side of it is service configuration. And I think the goal here is really if I have these knobs that are like, hey, how big should my connection pool size be? Right? Or, should I enable feature foo or enable feature bar, right? These might be things at runtime I want to turn, right? To say, okay, I'm going to trial feature foo, and if my site blows up, I'm going to turn it back off, right? But I don't necessarily want to redeploy the application for this. So the way Consul handles this is by exposing a kind of a hierarchical key value store, right? This is almost, feels like legacy to talk about sort of Zookeeper, but like 2012, that's what we would have done, right? You'd have your Zookeeper and you'd set these feature flags and turn on and off. But it's sort of the modern equivalent of that is the sort of hierarchical kind of key value store that lets you put those things in there, right? And then you can either poll against it. There's a rich HTTP API. You can do long polling, so you can get sort of edge trigger the moment there's a change, right? So if enable foo gets turned on, right, you can react to it sort of immediately, right? The more sophisticated use cases end up being around the ability for Consul to act as sort of a locking server. So you can actually use it to manage distributed locks, right? So if I have 5 services, but only one should be active at any given time, right? Let's say I'm architecting sort of an HA pattern. You can actually offload some of that complexity to Consul. So Consul can do that sort of leader election, say this instance is currently the lock holder and can process requests, and the other ones are sort of hot standbys. And so you see sort of a lot of sophisticated, sort of complex software built on top of it that is able to then use that to make the systems reliable. So there's kind of a lot there. Here's a really simple example of it though, right? So if we look at this command, what we're going to do is basically use the kv put to do a write. And you can see it's sort of a hierarchical sort of file system type layout. So under service web, we're going to just have a key called enable foo, write the value true, and we can come back and read that value and we get true back, right? The other way to interface with that is obviously the UI as well. So you could use that to manage the same set of keys. Or just maybe even to inspect them and, if you're trying to debug something, see what the current status is. So that kind of covers service discovery and service configuration. The next piece that's sort of, in some sense, the relaunch of Consul in the last 2 years has been the connect piece, which is really looking at, that segmentation component that historically was sort of exercise left to reader, right? And so when we talk about connect, there's kind of 3 key pillars, right? One is what are the set of rules that we manage, right, which we call the service access graph. The other is certificates and how those sort of play a role. And the third piece is, okay, great, we have all these rules. How does this actually integrate with the end application, right? So when we talk about the service graph, that's really the set of policy around who's allowed to talk to who, right? What are the set of allow, deny rules, right? And as you saw, Tim sort of showed us, effectively it's a shift towards source and destination service. So we say web server is allowed to talk to database, right? What we don't say is IP1 can talk to IP2, right? And the reason that shift is so important is because now it's scale independent, right? If I say web can talk to database, it doesn't matter if I have 1, 10, 50,000 web servers, the rule is the same, right? Versus if I say web can talk to database, but I translate that to a firewall rule, if I have 50 web servers and 5 databases, it's 250 firewall rules, right? And if Kubernetes decides to move a web server around, well, guess what? You're changing that firewall rule. So you start to get into this world where your rule set is actually very closely tied to sort of a thing that we would think about as a detail, right? You know, it's a detail what node Kubernetes puts the pod on, I don't really care, right? But I do care if I'm managing a firewall, right? Because now that IP does matter to me, right? And so that becomes a pretty annoying impedance mismatch where you either have two choices. One, you accept that the firewall is just going to be permanently behind and you're always just waiting on firewall updates. Or two, you just give up on security and say just whitelist everything that's Kubernetes and whatever, I don't care what node it's on. Right? In which case, you know, it's kind of like, you know, you have a front door, but you never lock it. So you're like, okay, well, what's the point, right? So, you know, this is an important shift, right? We move to source and destination. It's much fewer rules to manage, but it's also, you know, scalable, right? We don't care now as we scale up and down as things move around, right? We're sort of shielded from that. And as, you know, Tim pointed out, you can manage this in a number of ways, right? The UI might be sort of the most friendly, but, you know, obviously CLI, API, Terraform, all that good stuff, right? So I think here's an example of what it would look like via the CLI, right? You can create sort of a blanket rule and just say, you know, by default web to anything deny, and then create a more granular override, right? Web to database explicitly allowed, right? But the goal is really to sort of see it's really a service that we're talking about, not a, you know, IP, right? And then the UI, you saw a similar sort of thing. You can go in and edit it and play with it there as well. So this brings us kind of to the second piece, which is great. You know, we've said we want to move away from IP and talk about logical service as the unit of identity. The problem is logical service doesn't exist on the network, right? What you see is IP1 is talking to IP2. You have no idea who's web, who's database, right? Like all this stuff is opaque. So the challenge becomes how do you reassert a strong notion of identity where you don't care about IP, right? And you don't necessarily trust the network. Well, it turns out that is exactly the problem definition of the public internet, right? And we've solved this with TLS, right? It's sort of the gold standard here. So what we really need to do is shrink wrap TLS to fit in the data center. And then you really get two kind of for free benefits, right? One is a strong cryptographic notion of service identity, right? I know the caller on both sides. But the other piece of it is encryption of traffic, right? This is, you know, also important as we talk about things like GDPR compliance, right? It's like we know these mandates are now here, but actually retooling every application to speak TLS is painful, right? So, you know, when we talk about TLS, the hardest part of it tends to be certificate generation and distribution, right? You know, I joke, but it's only half a joke, that the average certificate lifespan is always longer than the average employee tenure at a company, right? Right? And you all know, everyone laughing knows why, right? It's for a very specific reason. Like, I don't want to work here when it blows up, right? So, you know, that is always the case with TLS. And so, you know, when we started working on this, the core focus was, it has to be a focus on we generate the certs and do all the lifecycle management. Otherwise, if the expectation is you figure it out, it's going to be a disaster, right? It's like everyone will generate it for 20 years and then on the day, right, the whole everything explodes, basically, right? So instead, the moment an application gets scheduled with Consul, it's the Consul client that's actually responsible for generating a public-private key pair. That gets flowed up as part of a certificate signing request to Consul servers, which ultimately might forward on to Vault or Venafi or some external certificate authority to sign the cert and then flow it back. But the generation and then the re-signing and renewal is all managed by Consul. So Consul, you know, whatever, every 24 hours will generate a new certificate signing request, get it re-signed, flip over to the new cert, etc. So this is sort of always happening in the background because the goal is you have to make the cert management sort of invisible, right? Otherwise, it's the biggest pain point of the whole thing. So the certificates themselves are basically plain old X509, right? So if you go to, bankofamerica.com, and they hand back a cert, it's going to be almost identical to the one that Consul uses. The one sort of twist is we adopt this sort of spiffy specification, which is what Istio uses. It's what a few service meshes are sort of moving towards. The goal being that there's some hope of interoperability between these systems, right? They sort of have a common way of describing identity, but effectively it is a one field change to a otherwise standard X509 cert. Right, so now the next piece of this is great. We have the certificates, we can rotate those things all the time. What about the actual certificate authorities, right? Those things also tend to be an enormous pain, right? And they tend to have lifespans that are like 30 years because nobody wants to deal with that thing, right? And so we looked at that and said, anytime you're managing anything for 30 years, it probably has a smell to it, right? You probably shouldn't be doing that, right? It's only because it's easy, right? Or it's hard to not do it, right? So our view was, what if you automated even that thing's rotation? So with Consul, what you have is, classic PKI hierarchy, right? The root, intermediate, and then the signing leafs, which we're distributing to the apps. And at any time, you can basically hit the API and say, rotate the root, right? And so what we'll do is generate the sort of successor root and generate a cross-signed intermediary, right? So this will be signed by both old and new root, and all of the new leaf nodes that will sign will be signed by that intermediate, right? And so what this lets us do is, for a period of time that we're in transition, systems that are either on old C8 or new C8 can both validate that certificate, right? Both are valid because of the cross-signing, right? But because we know everything we generate is short-lived, Consul knows it's never going to sign something more than 24, 48, 72 hours. Based on the config, we know, okay, if we wait 72 hours, everything by definition generated by the old root must have expired, right? Because we didn't sign anything longer than 72 hours. So what that, why does that keep happening? So what that lets us do is then after 72 hours, basically kill off the old system, right? We just flip over entirely into the new root, generate a new intermediate, and all the leaves go out under the new root, right? So this lets us start to move to a place where even things like the root CA might only live for a year, and we can just constantly rotate those things, right? Because who cares, right? We can automate it in the background, just because we don't really have to think about the leaf themselves, right? Those things are also going to be automated. So that kind of brings us to the third piece of this, which is great. We have our policies in the form of access graph. We said web can talk to database. We have identity in the form of certificates, right? But what about the data path, right? You actually need to sit in front of the applications, otherwise, great, all the rules are not that helpful, right? So there's really only two answers here, right? Answer one is, as you'd expect, Consul aware. Answer two is Consul unaware, right? So how do we do this in a Consul unaware fashion? It's basically through a series of sidecar proxies, right? So these will run alongside the application. We don't need to make code changes to the app. And what it gives us is operational flexibility, right? Apps don't need to be retooled. They don't need to know about Consul. We just deploy them alongside. Everyone's none the wiser, right? And so what this tends to look like is something like this, right? Within, this could be a VM, could be a pod, right? Could be some unit of deploy, right? You'll have the application, and it'll be co-located with both the proxy and the Consul client, right? The Consul client is providing configuration information or control data, and then the proxy is actually in the data path, right? The black lines, right? So no traffic is flowing through Consul. It's flowing through the actual proxies, which are make up the data path. What those proxies actually are, in some sense, you pick, right? So we have first-class integrations with Envoy. There's HA proxy, there's Nginx, there's all sorts of kind of options there. There's a built-in one that we ship with that's just out of the box. So there's a bunch of kind of choices here, but the point is that the control plane and data planes really are distinct, right? You can kind of mix and match these things as you choose. Here's sort of a simple kind of configuration of what it's like to define sort of an upstream. So here we're going to define and say, hey, if my app talks to local port 1234, I want that to upstream me to Redis. And so what that means is from the local app's perspective, when it gets deployed, it looks something like this, right? The app just then talks to localhost 1234, and because we've defined our upstream goes to Redis, the proxy knows, great, incoming connection 1234 means do the service discovery of where Redis is running, connect to Redis, and do the load balancing against that, right? Another kind of interesting sort of challenge with these types of technologies is what about sort of end users, right? If I'm a DBA or I'm a developer and I need access, let's say, to the database, historically I jump on the VPN, and then I'd be able to just pSQL into the database, right? But what happens in this sort of an environment when it's secured by this, right? So what we sort of thought was, a nice abstraction for this is almost what we had with SSH reverse tunnel, right? If I need to get on a box, I can sort of do a reverse tunnel and then, point to the localhost port, and I can use that to get onto it. And so it's almost the same sort of syntax, right? As you can use the Consul connect proxy command and basically say, I want to connect to my Postgres upstream and bind that to local port 8181, right? And then I use my normal command line tools like pSQL, right? And I say, great, connect to localhost port 8181, and it operates almost like an SSH reverse tunnel. So for my laptop, I have the proxy that's listening to port 8181 and then doing the kind of connect protocol to take me back to the database. So I can still do my normal development flow and use my normal tools without totally breaking everything. And now I need all my tools to be sort of connect aware, right? Which would be a nightmare. So the other answer, if we're sort of not oblivious, is to be aware, right? Is the native integration, right? The nice thing here is effectively what we're doing is plain old TLS. Right? There's really almost nothing special happening here. So there's really almost no overhead to just doing TLS. If your app is doing TLS, making it do Consul version TLS, there's really no difference, right? The only challenge is it does require code modification, right? So this is why it's high touch relative to Sidecar. So here's an example using the Go SDK. And basically you can see there's sort of the preamble to set up the SDK, right? Defining the API client, declaring our actual service. And then the only real change to the sort of existing logic is this one line to say, source the server's TLS config from Consul, right? And what that lets us do is actually hook into the point where you need a certificate and are accepting connections, right? So underneath, behind the scenes, what that's doing is Consul's now then going and generating the certificate, and there's a background thread that's basically periodically getting the new certificate the app is using, right? As well as things like the certificate authority. The other piece of this, and where I said there's a small performance difference, is anytime we accept the connection, we have to validate against Consul. Should I accept this, yes or no? Right? So great, I'm the API service, I got an incoming connection from web. Before that connection gets handed off to the app, the SDK basically does the callback to Consul to say, I saw a connection come in with that matches the signature, yes or no, right? And so that's where there's that on connection establishment, there's the slight additional overhead over plain TLS. The moment we've accepted the connection, it is plain TLS. There's no difference. It just is TLS at that point, right? And so that's why there's really not much a lift required to be natively integrated. So just quickly recapping Connect, there's kind of these three main pillars, right? One is what's the set of rules that we talk about, right? And that's what we call the service access graph, and it's this shift, sort of physical IP to logical service identity, right? Then you have certificate distribution, which is really the heart of how the system works in terms of identity and security, right? And then there's app integration, where you have two choices, either aware with an SDK or unaware with a sidecar, basically. So that's kind of the sort of, I guess, high-level theory about it, sort of translating it now to architecture. How does the system actually look and work and function? Consul itself is basically delivered as a single binary, right? And you can either operate it in server or agent mode, right? In practice, you have 3 to 5 servers per data center, and you might have sort of n number of data centers, right? Some people have 30 plus data centers. So you can sort of pick, and you just run a set of servers per data center. The servers are sort of the brain of the system, right? They have all of the real state information that's being replicated between the different servers. They'll do sort of leader election and automatic failover between them. And they have really all the main data, right? The service registry of what's running where, the actual rules of who can talk to who, the key value data. When you start getting into multi-data center configurations, they're the ones that are forwarding traffic between data centers. So they're really pretty much the sort of control center for the whole thing. The clients, on the other hand, sort of run everywhere, right? They're on every node, they're in every pod, etc., right? And their goal is really a few things, right? One is they expose the HTTP and DNS API to the local sort of applications. So as an app, if you want to talk to Consul, you never sort of have to then first discover Consul to do your service discovery, right? Instead, you always talk to localhost 8500, and Consul's sort of there. It's the dial tone, right? So what this lets us do is that client is never actually doing much to service these APIs. It's just acting as a way to transparently forward that request, right? So you always dial localhost 8500, and then it transparently forwards to wherever the servers are running, right? So this lets us sort of shield clients from that, right? The other thing it does is locally register and monitor the clients, right? As well as do some caching of data. And we'll see why this is important. The big sort of reason, the sort of TLDR, and we'll kind of get to it in a bit though, is it lets us shift the architecture of Consul from sort of a pull-based model to a push model, right? Because the agent runs at the edge, it can notify the central servers when anything changes on sort of an edge trigger, as opposed to the central service constantly pinging and saying, are you alive, are you alive, are you alive, right? So if you've ever had to deal with like Nagios and trying to scale a Nagios deployment, you sort of know the pain there, right? A pull deployment, it's fine if I have 50 machines and I check every 5 seconds. Great, I'm only having to do 10 requests a second. The moment I have 1,000 machines on a 5-second interval, I'm doing 200 requests a second, right? You see, over time, it doesn't scale particularly linearly, right? These systems end up getting saturated and fall over. Versus if we can go to a push, there's enormous Consul clusters of 10,000 plus nodes that are effectively idle. Because only when there's a change do you actually need to interact with the server and say, hey, I've gone from failing to passing, or vice versa. So one of the key sort of aspects of this system is in the background there's kind of a lightweight gossip protocol taking place. It actually is a tool that is totally separate, so if you sort of like geeking out on that stuff, we have a tool called Surf you can run that's just a pure peer-to-peer gossip protocol. And what it really gives you is kind of two key features, right? One is cluster membership, so every node knows what is every other node in the cluster, right? So they can kind of maintain this information in the background. And the other is failure detection. If a node fails or leaves, we can efficiently broadcast that to everyone else. So this gives you kind of two important properties. One, when a server joins, it's really easy. The server just talks to any existing node, or really any node that wants to join talks to any existing node, right? And you can discover who all the other nodes are, right? So you don't have to have this complex bootstrap of any new client that comes up given the IPs of all the servers, right? It's like you join any IP of any existing node in the cluster, and you get the full catalog of who's running, right? The other thing is it has a little bit of background metadata around the versions of all the nodes and servers, so we can actually navigate sort of protocol upgrades in a really seamless way. And so you can run basically the initial release of Consul with the latest release of Consul in the same cluster, and it will work, because there's so much sort of protocol negotiation magic happening in the background, right? So that's nice when you start running large-scale clusters where it's impossible to upgrade the whole thing at one time, right? One business group might upgrade, but not another business group. The other side of this is the failure detection, right? So if a node leaves, we can make the distinction between having gracefully left or having failed, right? Crash, power loss, whatever, right? And so this enables a few things, right? If you've gracefully left, we can sort of cleanly delete you out of the catalog and not sort of populate it with a bunch of cruft and you have to go back and delete things that don't exist anymore, right? Now the reason we can make this thing scale so efficiently is because we don't have any heart beating in the system, right? This goes back to that gossip protocol of every node is involved in health checking every other node, right? So every second a node picks another random client, pings them and says, are you still alive? And if you are, you respond back to me and say, yep, I'm still here. And we say, great, right? If I don't hear a response back though, then I can flag and say, hey, I've suspected that you've died. And if I don't hear back in a little bit, we broadcast to the whole cluster, I think that node is dead, right? And so what this lets us do is offload the work of failure detection from the small set of central servers, right? There's only 3 or 5 of them, to effectively every node in the cluster. So this is what I mean is even if you have a giant cluster of 10,000 nodes, the servers are effectively idle because their primary work of sort of maintaining metadata updates and doing health checks has been sort of distributed out to the whole cluster. Right? So this is what lets the system scale so well. So if we kind of zoom out and look at kind of the 10,000 foot view of Consul's architecture, it looks something like this, right? Each of these data centers will have some set of servers, right? So usually 1 leader and 2 or more followers. And between them, there's data replication and RPCs flowing. And then sort of any number of clients, right? 1 to thousands, right? And so the clients and servers are all participating in gossip. And when the clients have a request, they need information, they make an RPC to the servers, right? So the servers have all the state and can actually sort of respond, right? If we need to make a cross data center request, the servers will then, it'll go client to server, server to the other data center. That data center will service it and forward the response back, right? So clients never really talk cross data center, only servers do, to restrict the amount of kind of cross traffic that takes place, right? And then each data center looks like almost a mirror image of each other, right? And the sort of very much by design is if I lose one data center or I lose the link between these things, each of them is an independent failure domain, right? Each data center will continue to function independently even in the loss of another data center, right? As opposed to if we had to go across to the other side and we lost that side, both data centers are now host, right? Cool. So I think one thing we touched on, but it's worth just sort of repeating, is this sort of distinction between control and data plane, right? So when we talk about Consul, its role is very much control plane, right? It has the metadata of who's running, what are the policies, what are the configurations, etc. And it's pushing that configuration down to the data plane, which is then ultimately responsible for the communication, right? And that's designed to be pluggable, right? So that could be Envoy, could be HA proxy. In some cases, actually, like F5 hardware firewalls are Consul aware, right? So if you have an F5 hardware device, you can actually point it to Consul as a backend and it'll auto-populate what it's load balancing to, right? So this is part of the goal, is to think about this distinction of, you can have this sort of hybrid data plane of hardware devices, software devices, full service mesh, right? And in practice, many organizations probably will, right? Because it's very hard to go atomically from one universe into the next. So this is kind of the core look of the data path in a service mesh world, right? Is again, the Consul clients are pushing down configuration to the proxies. The proxies actually do traffic, and the apps are sort of going back and forth transparently through the proxy. They're sort of none the wiser, right? So you saw an example of how this can work with Kubernetes. It's sort of the high level view. You basically run the agent sort of across each host so they can do that sort of gossip and registration and caching locally. And there's many ways of doing this, right? You can just use a daemon set with Kubernetes. You can't, and then the proxy does need to be per container or pod, not per host, right? And the reason for that is otherwise it's impossible to distinguish where the traffic's coming from, right? If I have 5 apps running on the machine and only one proxy, and traffic hits the proxy, it doesn't know which of the 5 apps are the origin, right? Versus if we run one proxy, one app, then it's very clear, right, who was the source of traffic. Cool. So when we talk about Consul, it's really, the goal is it's a very much batteries included architecture, right? It doesn't have external data sources. It has its own built-in proxy if you want to use that. It'll do multi-data center. It'll go from 2 nodes to 20,000 nodes, right? So the goal is really that it's sort of all self-included and designed to be sort of highly scalable and available out of the box, right? Because this kind of stuff you're running as your core network control plane, right? Like when it goes down, it takes your whole data center with it, right? Which is, means you actually have to care a lot about things like availability for these things, right? So sort of just quickly wrapping it up, right? Our view is kind of this infrastructure is very much sort of a means to an ends, right? And when we talk about this kind of microservice architecture, that set of operational challenge we've talked about sort of as we do that transition is the exact same for everyone, right? And so, what we tend to see is sort of a patchwork type solution of reinventing this wheel. But ultimately, that's going to end up with a whole lot of long-term maintenance debt, right? And so our goal really with Consul is like, how do you solve that wheel sort of once, right? I think the common wheel of problems with any microservice architecture is these 3, right? How do these apps find each other and do discovery and routing? How do you configure these services in an online way? And how do you then segment access so it's not sort of exercise left to reader at the sort of network level? And that's it. That's all I had. Thank you guys so much. Happy to take any questions.
What does the data path look like for doing a cross data center Consul connect mesh route?
Super good question, and it's an evolving story. So today, basically the expectation is you have some sort of VPN or interconnect or whatever that allows the traffic to flow in a relatively flat way, right? So Consul will resolve it to an IP. So if I say, an app in data center 1 requests, tell me about Redis in data center 2, Consul will just return the IP to it. The assumption then is that that IP is routable, right? So if it is, you have a flat network, you have a VPN, you have direct connect, whatever, then it just works. But what happens if I don't have a flat network, right? Like what if I have an AWS and a Google account and they're not even connected? There's no VPN at all. How does that actually function? Where we're going towards is this notion of what we're calling mesh gateways, right? So you'd actually be able to run these gateways at the edge of your network, and we'll actually do multi-hop routing to get there. So you can say, hey, between these 2 things, you must go through a gateway, and Consul will kind of force the jump of talk to gateway 1, which will route to gateway 2, which will take you to the app and back, basically.
So if I were routing between multiple Kubernetes clusters because the multi-cluster story in Kubernetes is awful, then I probably need to run internal load balancers for now.
Or exactly, right. And then where this will go is you'll run the gateways internally.
Right.
So you could run a mesh gateway on the sort of edge of your Kubernetes cluster, and then Consul will basically gateway it across between those things. Yeah, so I'm excited. That'll be cool. You heard it here first. Cool. Other questions?
So, From what I understood from the architecture, and I'm very new to this stuff, you can query any of, say, the servers for the state of the system, right? So, what is the guarantee on the consistency? So, suppose I do a dig on 2 different servers somewhere.
Yep.
Am I guaranteed to get the same information?
Got it. Super good question. So basically with any query you make against Consul, you can actually specify what level of consistency you want. So there's 3 levels that Consul exposes. One is strict consistency, which is it must be the currently serviced leader of the cluster must answer me with the latest result of the cluster. That's the strongest guarantee. But the challenge with that one is there's a scalability challenge, which is you're saying my request must go to the leader. There's only so many cores that the leader has. The next consistency mode is sort of the default mode, which is slightly weaker than that one. It still does have to flow to the leader, but the leader doesn't have to re-verify that it's still the leader, right? So there's a brief 100 millisecond period where, let's say another node has been elected leader and that node doesn't yet know about it. No transactions could have occurred, right? So it's a very, it's pretty much the same as strict sort of consistency, but much higher performance because I don't have to do a double check of am I still leader on every request, right? Then there's what we call sort of stale mode, which is your request could be serviced by any server, right? And in some sense, that's allowed to be arbitrarily stale, right? Which is the current leader is always the most up to date. The other servers might be arbitrarily behind, right? In practice, they're usually within milliseconds of the leader, right? So they're very, very close. So a common pattern of a lot of our tooling uses the sort of notion of max stale. So you might say, I'm willing to do a query, but I don't want a result that's more stale than, call it 5 seconds, right? If it is older than 5 seconds, I don't want your server's answer take me to the leader, right? So with that pattern, basically, you can sort of bound and say anything older than 5 seconds, I'm going to guarantee that I'm going to go speak to the leader. And so you kind of have this knob to play with. Out of the box, I think what we do with the DNS-based service discovery is the 5-second max stale. So we'll say you can go to any leader, you're guaranteed to be within 5 seconds of the leader, and then otherwise we'll just route you to the leader if it's older than that. But yeah, good question.
But so that's one aspect. The other one is this gossip protocol itself is probably probabilistic, right?
Yes, yeah.
So the leader itself may not have got the latest information because it's not gossiped into the leader yet.
Totally, yeah, you have a strong intuition for this, yeah.
So how do you, what's the sort of parameters you set on that gossip protocol so that it gets with very high probability to everybody?
Super good question. Yeah, super, you've spent some time with gossip and networks, I'm gonna guess. Basically, there's sort of a few answers there, which is one, the system is very conservative in its defaults, and so by default, it will sort of tend towards a message being repeated within the network, something like 7 times over, right? So we're going to rebroadcast the same message around a node joining or leaving to a pretty high extent. Every node will expect to see the same message 7 times redundantly. The other thing we do is we'll basically pick a different set of peers every time that we're broadcasting, right? And so it'll take different paths through this network, right? Layered on top of that, there's an anti-entropy protocol, right? So we'll do the efficient hot path gossip, which in practice, even on clusters of 2,000 plus nodes, is sub-second. But then on top of that, there's a sort of long-run reconcile process. So every 30 seconds, you'll pick another node and do a full TCP state sync of hey, what's the last 1,000 messages you've seen? What's the last 1,000 messages I've seen? And they'll sort of do a replay of those messages. So even if you have these networks that get partitioned, right? I have 1,000 nodes that can't talk to these 1,000 nodes. Each will continue to function, right? This 1,000 will declare that 1,000 dead. This 1,000 will declare the other 1,000 dead because they can't communicate, right? The moment that thing heals, they'll rapidly realize they're getting messages from the other side and basically kick off an anti-entropy repair and then basically restitch that actually the other side is still alive, basically. So they'll sort of do that sort of recovery and come back together pretty quickly. But yeah, Surf is actually an independent tool that you can go kind of play with, and there's sort of a simulator on the website of its knobs you can play with, of cluster size and propagation delay and things like that, so it's kind of neat. But yeah.
Thank you.
You illustrated lots of full mesh topologies. What's Consul support look like for partial mesh topologies?
Yes, good question. So this actually hangs off of the same mesh gateway concept. So one of the directions we're going with is this notion of or what we're calling sort of a terminating or a non-terminating gateway. So in default, the kind of mesh topology I described those mesh gateways are really pass-through, right? You're going to go from proxy to proxy in sort of an end-to-end way, and all the sort of center gateways are doing is they see TLS traffic, they forward it on as continues as TLS traffic, they never decrypt, right? What happens if I have an endpoint that doesn't speak connect, right? Then I actually do potentially want to terminate the TLS at the mesh gateway point and have the gateway dump it back down to plain TCP and take it to the end application, right? So this lets you sort of have the on-ramp and off-ramps on kind of both sides. As an app that doesn't speak or can't have a proxy locally, can sort of on-ramp in by speaking TCP to a mesh gateway, which brings it in as TLS. And on the other side, you can sort of off-ramp it by terminating the TLS and bringing it out to an app. So I think in practice, what you'd see in the sort of hybrid modes is, the new greenfield stuff would have actually the Envoy sidecars locally and would terminate at the edge. Versus if I'm going out to a legacy, mainframe, let's just say, I'd run a terminating gateway in front of it. So anything will go all the way to the gateway, that's responsible for the authorization. It would then terminate and then take it out to the mainframe, which has no idea.
I was more talking about like partial routability, so some subsection of nodes can't talk to some other subsection of nodes, but those nodes should still be able to talk to each other via the mesh kind of around their partition.
Oh, I see what you're saying. Yeah, so from a gossip perspective, we'll work around that because we'll take multiple paths.
Yeah.
From a routing perspective, you'll just have to configure almost with the same way you'll do with the mesh gateways of saying, hey, what subset can talk to what subset? You would just force it and say, this route must transit through a gateway, basically. And the gateway would act as that sort of redirect point around whatever the elbow is.
It solves a lot of PCI problems.
Yes, totally. Yeah, that becomes the goal. You run just a gateway at the PCI entry point, and then the firewall has one open port. Exactly. Yeah, I'm excited for it. Cool. Yeah.
Regarding consensus problem, how do you compare Raft versus Paxos, and why Consul basically chose Raft?
Oh, it's a tricky one. Okay. Yeah, so the question is sort of why Paxos versus Raft, the relationship between them. In some sense, Raft itself is Paxos, right? The difference between the two is the core design of Paxos is sort of like on every decision point, you would run the Paxos protocol to come to a decision, right? So on every change, right? One way to simplify it is every time I wrote to Consul, right, you'd run a round of Paxos to say, okay, this write just came in, do we agree on it? Yes or no, should it take place? Okay, if we agree, then we do the write, right? Versus what Raft really simplifies and says, A, that protocol is like very slow and expensive to run, and B, for the most part, right, you're not going to have 20 different points making conflicting decisions, right? So what's easier, and what Raft does is you run Paxos and elect a leader, effectively is what the system's doing, right? So the first decision you make is, who's our leader? We have 3 servers, one of us should be leader, right? The moment you elect a leader, then the leader's job is to basically just stamp an incrementing count on each transaction. So this is write 1, this is write 2, this is write 3, this is write 4, and replicate it out to the followers. So that the cost per write is much cheaper, right? The expensive coordination takes place infrequently, not once, but anytime you need to elect a new leader, you run Paxos effectively and elect a leader. And then the writes are relatively efficient, right? Because the leader just basically, adds an incremental timestamp and replicates it out. If the leader dies, then you rerun Paxos and pick a new leader. And there's some nuance around how you make sure you do sort of data playback and things like that. But effectively, that's the kind of the heart of it, is you're still doing Paxos, you're just doing it infrequently to elect the leader and then serialize writes. Yeah. So the reason for it is A, it's much simpler to sort of implement and debug, but B, in practice, it's higher performance. So it's closer to something like multi-Paxos. But that's definitely, we're getting in the weeds.
No, I'm just curious because when reading about like XSD versus Consul, they say that we are more scalable about Consul because we're using Paxos.
Yeah, they also don't benchmark reads, so take the benchmarks with a grain of salt. It's like Mongo, all databases are fast if you don't worry about persistence to disk, right? Yeah. It's like if that's a detail, then
When are we going to see Consul become a KV option for the Kubernetes project?
Oh.
For the love of God.
It's a very political, I would say, decision, very not technical. So the technical work was done years ago. The pull requests might still be open. So I think Cisco actually funded it. They had a partner actually just do it, and the pull request sat there. And it's a long story around that one. So I think the short answer is never. We can dream. Cool. Other questions?
Any other new features that you're excited about coming up that you can talk about?
Well, I already gave you one spoiler. That's enough. There's many, but there's some conferences coming up, so you gotta save the good stuff.
When can we see Consul connect, like native integration and Nomad?
That's a good question. I know we're a bit embarrassingly behind there. The next major version of Nomad that's on the roadmap, so .10. Yeah, good question. Cool. Awesome. Well, thank you guys. Oh, one last one. Yeah.
When's Terraform 0.12 coming out?
Hey, we just shipped the beta. The beta is out. The beta is out. So the faster you report bugs and we sand down the edges, the faster you get released. But honestly, the beta is really, really good. The team was a perfectionist about the beta, so we had to force them to finally ship it. They're like, we're not going to cut a beta until every single test passes. You're like, that's a release candidate, not a beta, right? Like, so, the beta with, exception of a few edges, right? I wouldn't run it on production infrastructure yet. Its biggest edges are the upgrade from .11 to .12, right? But if you're on, so I'm just going to do a project pure greenfield on .12, it actually is really solid, right? So the edges we're ironing out are all around upgrade scenarios between the two. So if you try it out in the kind of greenfield stuff, things you don't worry if .12 sort of rough around the edges, it's actually working super well. So we're feeling good about .12. Cool. Thanks, guys. Thanks for being here.